So where I ended up in my last lecture, that was the theorem. What was the theorem? The theorem was like that okay, yes, yes, that if P be a local homeomorphism from a space E into another space B such that it is a surjective map, and if E be a locally path connected space and B be a locally simply connected space, then you see that the two concepts are equal. That is, if P is a covering map, if and only if it admits path lifting property. And in my previous lecture, I have already proved the if part, that is if P has path lifting property, then it is a covering map. Yes. And for the only part, I have already proved the lemma where I finished my lecture. That is the lemma which tells us that if P be a covering map from a space E onto B, such that if we fix up a point E naught and its image by B naught, that is P naught is B naught, that you can see in the picture, and any path alpha 0 1 to B which starts at B naught. So this is your alpha. Yes. So this alpha has a unique path lifting alpha tilde in E which starts at E naught. That is where we fix up the point in E. So that is the lemma, and with respect to this lemma, you definitely have this only part of the corollary, this result. Because if P be a covering map, then you definitely have this path lifting property, although you do not need these restrictions. That is, just you take E and B, and if P be a covering map, then you definitely have this path lifting property. So in particular case, for this case, it happens. So therefore, this theorem has been proved. And not only that, while proving this theorem, I have already proved this lemma. This is an important one. That is a covering, if you have a covering map from a space E to B, and suppose you fix up a point E naught and which goes to B naught, then any path alpha which starts at B naught must have a unique path lifting alpha tilde in E which starts at E naught. So that's Homo has been discussing on that. You need to fix up the point E naught. That is crucial, because there are several many lifting, but once you fix, then it is fixed. Then the lifting is fixed. This is unique. Okay. Sorry. Yeah. Okay. Fine. So today I shall just doing the same thing for path homotopy cases. That is, let us first write down the statement. That is, the result is like that, that if you have a covering map, be a covering map, and then you need to fix up one point E naught, and let us denote the image of E naught under P by B naught. Then if you have a function from the unit square I cross I to B, so be a continuous map with okay, be a continuous map with the condition that this will be B naught, then you must have a unique path lifting. Then you must have a lifting. Then you must have a lifting f tilde of f satisfying that at the point 0, 0 it must be E naught. And in addition to this, if you consider f to be a path homotopy, then so is its lifting. So is its lifting. So this is very important one, that P be a covering map with the restriction that at the point E naught its image is B naught. Now if you are given a continuous map F from the unit square to the B with the condition that f of 0, 0 is B naught, then you must have a lifting if this is unique. Yes, then you must have a unique lifting f tilde of f satisfying the property that f tilde at 0, 0 must be E naught. If in addition f be a path homotopy, then so is f tilde in B. Okay. So how to get this result? What will be the procedure to prove this theorem? The process and the arguments are similar to those that I have already used in the previous result. Just using connectedness, you can, and also compactness of the unit square, you will get this. But let us take a visit of this proof, because these are very much basic things that you need to understand. So if I write down the picture of this proof, then what will be the scheme of the proof? Just I am taking, yeah. So this is your unit square. Then suppose this is your U. What is U that I should mention? And this is the slice where you have chosen the E naught, that is P E naught is B naught, where that is E naught is in P inverse B naught. So I have already told you that P inverse B is a discrete space, and in each slice it must have at exactly one point. So if E naught belongs to P inverse B naught, then that E naught will be in one slice, exactly in one slice, and that slice I have chosen it at V naught. right? Then what will be the scheme? Just so I need to mention the cover, that is since I cross I is a compact space, then by the same arguments applied to the previous lemma, using that one you can definitely have this covering, just using compactness and the property that P be a covering map. Yes. So this is a finite cover of I cross I, such that for every ik there exists an evenly covered neighborhood u naught or u, suppose it is u, okay, okay, let it be u naught, subset of B satisfying the property that f of this small square this is going to be in the set u naught. Okay, fine. Or I can denote this by, okay, fine, I can denote this by suppose it is I comma k. Yes. Oh. Okay. And let us suppose that, let us start from the square, this one. This is your trick. You need to start from that square. And this is your 0, 0. And you have already specified the value of f at 0, 0, which is b naught. So this is your f. So you can cover this one. Yes. Yeah. Just first one this and then go to that one. So this is the pictorial representation of the proof. Yeah. And similarly, you can have this here too. Okay. Yeah. So then you just cover this one and then go to this, and then this one, and like that. So you need to start from this square. That is, you need to start from 0 S1 cross 0 T1. And suppose that it is in U naught, say U naught. And since E naught belongs to P inverse B naught, now what is B naught? That is F00, 0. Then define F tilde at 0, 0 is equal to E naught. So this is your trick, and you need to fix up the point, and you need to define F tilde of 0, 0 at F tilde of 0, 0 will be E naught. So that means, so suppose this E naught is in the slice V naught. So that means F tilde of 0, 0 is in the slice V naught. So this belongs to V naught, say. Okay. Now, in order to make f tilde continuous, the image of a connected set must be connected. So, thus, since this small square is a connected set, so f tilde of this set, so it must be connected, and since f tilde of 0, 0 is in V naught, so it is in this one. It will be contained in V naught. And using this one, you define this on this small square. The definition will be that since it is a slice with respect to the covering map P from E to B, so P restricted to V naught to U naught, it must be a homeomorphism. So with this argument, you can define f tilde of s comma t as P restricted to V naught inverse as P restricted to V naught inverse of f s comma t, right? So you cover this first small unit square. Then you go to the second one in the bottom line, this one. That is, you consider the segment, the unit square, the square, the small square. So consider S1, S2 cross 0, T1. Then in the same way, there is again evenly covered open neighborhood U1, such that f of S1, S2 cross this, f of this small square will be contained in this U1. And definitely each point of, so if you take the corner, that is S1, T1, then you can say that each point of P inverse of f S1, T1, so it is contained in a different slice of the disjoint open sets. Suppose W beta be the partition which with respect to which U1 is evenly covered. That is, if you take W beta be the partition of the open neighborhood U1, then each point of this set will be in exactly one open set W beta. Suppose it is in W naught, then you define again. So define this one as, again, since W naught is a slice, then P restricted to W naught from W naught to U1 is a homeomorphism, and with respect to this homeomorphism, you can define this map as P restricted to W naught inverse of FST. So this covers the small square S1, S2 cross 0, T1, and then you go to the next one. Now, since the number of cover is finite, so ultimately what you do, so you first define f tilde in the same way as we have defined above for the entire bottom row, that is 0, 1 closed interval cross 0, T1. And then you define f tilde on one rectangle at a time vertically from the bottom row until f tilde is defined for all of I cross I. And since the number of such small squares are finite, so you can definitely achieve the goal. So thus, once we choose the value of f tilde at 0, 0, then f tilde is completely determined. And for this reason, f tilde is unique, because if you define another one, but you define the value of the function at 0, 0 be the same as that of f tilde, then these two maps will be unique. In addition to this, that I have already this is your P naught, yes. Okay. Yes. In addition to this, if A be a path homotopy, then what will happen? Then our claim is that f tilde is also a path homotopy. But why? Because if you take this left edge, then what will happen? Then this left edge will go to the point B naught by the map F. This is your f tilde. Yes. Okay. So this left edge will be mapped to B naught by the map capital F. And since f tilde is a lifting of F, so f tilde will carry this edge into P inverse B naught. P inverse B naught. But in P inverse B naught, you have discrete topology as a subspace of the space capital E. And so, which says that f tilde of this left edge being a connected set in P inverse B naught, and P inverse B naught is a discrete space, so that image is a singleton set. So that image is a singleton set. So I can just so f tilde of the left edge of the unit square is a singleton. And in a similar manner, you can show that the same thing will happen for the another one edge. This one. So this is a singleton. So that means f tilde is a path homotopy. Okay. And using this, you will have the following corollary, that if you have a covering map from a space E to B with the condition that with specifying the point D naught and its image by B naught, you have for any two paths FG, suppose the two paths lying in B from B naught to B1. Suppose F and G be two paths in the space B, which starts from B naught and ends at B1. And F tilde, G tilde be their respective liftings in the space E, which begins at E naught. So be the respective liftings in E which begins at E naught. Then what will happen? What is your conclusion? Conclusion will be like that. So if these two paths are path homotopic in B, then so is their liftings. Not only that, these two liftings f tilde and g tilde of f and g respectively, they will end at the same point, at the same point in E. Okay, so that means so if you have a segment this, and suppose this is your B and this is your E. So suppose you have two paths from B0 to B1. So this is your F and this is your G. If F and G are path homotopic, okay, and then their liftings, what will happen? So they are lifting F tilde and G tilde, they will end at the same point. So they start at E naught and they will end at, suppose, F tilde 1 equal to G tilde 1. This is your F tilde, G tilde, and not only that, they are path homotopic. Yes. So this will happen. Why? So the sketch of the proof will be like that. Now since F and G are path homotopic, so you can have a path homotopy. So suppose it is F from the unit square to B, be a path homotopy. Right. Fine. Path homotopy between F and G. Okay. And since it is a path homotopy, so f of 0, 0 must be B naught. That is where the map P map to B naught at the point E naught. Yes. This. Yes. Okay. And let this f tilde be a lifting of f to the space E. That I have already proved in the previous result. So this is the lifting of f to the space E such that at the point 0, 0 its value is E naught. And also in the last result you have proved that if f is a path homotopy, then so is the lifting. So f tilde is also a path homotopy. So therefore, being a path homotopy, f tilde of the left edge will go to E naught, since it belongs to the set P inverse B naught. So therefore, it is E naught. Okay, and this one you have proved that is a single one. Suppose this is E1. Let it be E1. That is, this is your E1. Okay. So now the restriction f tilde at I cross 0. What is I cross 0? That is the bottom edge of the unit square. So then this is a path. So this is a path in E which begins at E0. Begins at E0. Since f tilde of 0, 0 is E0. So this is a path in E, begins at E0, and this might be a lifting of the path f restricted to I0, I cross singleton 0. Okay, but by the uniqueness of path lifting, what you will have now, what is this? F restricted to I cross singleton 0. What is this? It is the path f, because f is a path homotopy in between f and g. So for the bottom edge, it will give you the map f, and for the top edge, it will give you the map g. So this is your f. This is your f. So by the uniqueness of path liftings, so you will definitely have f tilde of S naught is going to be this. And in a similar way, by imposing similar arguments, you will have this one, right? So hence, so therefore, f tilde and g tilde will end at where it ends. Now since these are equal, because you have already proved that this is a singleton set, and this is E1. So this is E1. So therefore, what is this? This will be your this. And what is this? This is your G tilde of 1. So it is E1. So F tilde and G tilde, they end at the same point E1. Okay. So using these facts, you will have the following map. So I can set up a okay. So I can set up a map from okay, let us take first a covering map from the space E to B. So be a covering map, and we specify one point B0 in B, and in P inverse B0, let us suppose that let E0 be such that E0 will be mapped to B0 by via P. Then what you do? So you do the thing is that suppose you have a you have a class F of loop F based at B naught. That is, you are considering the fundamental group of B based at B naught, right? That is, so let us, it's better to do it pictorially. Yes. Okay. So this is our E, this is your B, and this is your line and the segment 0, 1. Then you take B naught, and this is your E naught, suppose. Okay. B. So this is E naught, and this is your B naught. And you take a loop F, right? Then that is, this is F. So this F, this F has a lifting in E which starts at E naught. So F, the lifting of F in E, which starts at E naught here, right? Then we define a map, from the fundamental group of B based at B naught to the set P inverse B naught. By the rule, that is, phi of this class will go to the end point of F tilde, that is F tilde 1. That is, phi of this one is defined to be the end point of the lifting F tilde of F, of the loop F based at B naught. Now, since F is a loop based at B naught and F tilde is a lifting, so actually P of this one, what will be this? This is P compose, sorry. P compose of F tilde 1, and this is your F1. And what is F1? F1 is B naught, right? So this is the, so we define this phi of this as the end point of F tilde 1. Now you can say that, is it well defined or not? That is, if you have two loops that are path homotopic, that is, if you take two loops, suppose F star, that are path homotopic to each other, so then definitely your classes are same. Your classes are same, and by the previous result, you can conclude that these two liftings are also path homotopic, and they will start from E naught. Not only that, the conclusion is that these two lifting will end at the same point. So, and they will end at the same point. That means your F tilde of 1 is going to be F star tilde of 1, and which gives you the property, which gives you that phi is well defined. Fine. So you have defined a map from the fundamental group of B based at B naught into the set P inverse B naught, which is a discrete space in E, right? So now okay, you need to submit the assignment of Leavitt path algebra through email, through my email ID. Okay, you need to submit this assignment before 1 p.m. and just mail me at my email ID. Yes, okay, fine. Okay, so this is well defined. Fine. Now, so this is, so this phi is called the lifting correspondence. So called the lifting correspondence. Lifting correspondence determined by, so how do you get this one? Just by using the covering map. So determined by a covering map. P from the space E to B. And this correspondence depends on the choice of the point E naught that you have seen in the definition, that we have chosen a point E naught satisfying this one, which map to B naught. So this correspondence depends on this choice. Okay. Now, if in addition to this, suppose you have a path connected space, the domain space be path connected, then what do you see? Now, if the domain space be path connected, then you see that suppose you have another one, E1. You have already fixed a point E naught, and now you fix up another point E1. So you have 2 points E naught, E1, which is mapped to B naught via P, right? Now, since E is path connected, so you must have a path F tilde. So there exists a path, this, which connects E naught and E1, right? Right? And then using this F tilde, you see that if we compose this F tilde with P, then this map is a loop in B at B naught, right? Okay, so that means phi of the class of this, what will be this? So this is the end point of F tilde, because this is the lifting of this loop in E, and this lifting starts at E naught, ends at E1. So this will be your E1. So what did you get? So you get that phi is a surjection. So if you impose one condition to the domain space, which has been assumed to be a path connected space, then you will have a surjective lifting correspondence, right? Now, if you restrict the domain space into simply connected, just using another property, that in addition, if E is simply connected, then what will happen? Okay, so what will happen? Then you see that just take two loops f and f star, and with respect to which f and f star, with respect to which phi of class f equals to phi of class f star. That means they are lifting will have the same endpoint. Now, as you know, if you have a simply connected space, then uh, uh, then you have, if you have two paths which starts and ends at the same points, then they will be path connected. So this f tilde and f star tilde, these are paths in E which start at E naught and ends at the same point. So therefore, f tilde and f star tilde, they are path connected. Sorry, they are path homotopic. And if you take the homotopy, if you denote the homotopy as f tilde, so a path homotopy between f tilde and f star tilde, then you can conclude that if you compose this f tilde with p, then this is a path homotopy between f and g. These are very routine checkup, and you can do this on your own. Okay, between f and g. So that means f is sorry, f and f star, sorry, f and f star, so their classes are same. So this proves that this phi is actually, so it becomes 1 1. So thus, if you have a simply connected domain space and you have a covering map from the domain space E to B, specifying that P of E naught is B naught, then you can say that if the domain space is path connected, then the map, the lifting correspondence will be a surjective map. And in addition to this, if the domain space is simply connected, then the lifting correspondence will be 1 1. So if you have a simply connected domain space, and from that domain space to the space B with respect to a covering map P, then you will see that the lifting correspondence will be a bijection. So okay, so this is the corollary. You will have that if you consider a covering map, if you consider a covering map and suppose you have specified that P of E naught is B naught, so if E is path connected, then the lifting correspondence phi will be on 2. And in addition to this is simply connected, then this map will be 1, 1. Right? So the domain space, if we consider it to be a simply connected space, then with respect to this covering map, the lifting correspondence will be a bijection, right? So now is the time to compute the fundamental group of the circle, right? So our goal is to compute by S1 B naught. Suppose B naught is 1, 0. And our claim will be that this is isomorphic to the infinite cyclic group of integers Z plus. And actually this is regardless of the choice of base point. Okay. Okay. So how to get this one? Just by using lifting correspondence. Okay. So okay, fine. So the fundamental group of a circle can be viewed as the different number of revolutions that can be made around the circle. A double revolution loop cannot be homotop to a single revolution loop around a circle. Okay. So if you have two loops which wraps around a circle in a different number of times, then they cannot be deformed continuously to each other, and which indicates that the fundamental group of the circle based at B naught corresponds to an integer, that is a number of revolution, right? So it depends on the direction of loops that travels clockwise or anti-clockwise, which will determine the sign of the integer, right? Now recall that you have a covering map P from R to S1 that I have already discussed, and I have chosen this map as an example because this is very crucial. This is very important. Okay. So this covering map has been defined as it is known to you 2 pi I t belongs to R. So this is a covering map. Right. And now suppose you have a class in the fundamental group of S1 F. That is, you have a loop around S1 based at B naught. And note that with respect to this P0, suppose we consider we fix up this 0. So P0 is B naught. Then by the previous discussions, for this F, you will have a unique lifting to R. So F tilde be the unique lifting, right, of F to R, right? I have already give you some liftings, some examples of liftings uh, for this map. Yeah. Such that, so since it is a lifting, so we must have this. Yes. And so this map starts at 0, right? Since P0 is B0, B naught, so F tilde of 0 is 0. Suppose now, since F is a loop based at B naught, so its endpoint, the lifting, the endpoint of the lifting, it must be in this discrete space, P inverse B naught, right? Now, what is P inverse B naught? If you check and calculate, then what you shall get, that is you need to find out P belongs to R such that e to the power 2 pi I t is equal to B naught, that is 1, right? And I think you can do this on your own, and you will have that t are the integers. So actually you have P inverse B naught as your Z. This means that the endpoints of the liftings of each class will be an integer, n, right? So F tilde of 1 must be some integer n. That is, your definition is like that, so it is your n. So thus the lifting correspondence is actually a map phi from the fundamental group of S1 to the set Z, right? Now since P is a covering map from R to S1, and R has the property, that is, it is a simply connected space because its fundamental group is the trivial group. And being a simply connected space, what you can say about the lifting correspondence? That it is a bijection. Just by using the arguments, the observations I have discussed in the above. So to complete the proof, you need to establish that phi is a homomorphism between two groups, this one and this one. So this remains to check. Okay. Okay. So how to get this? So to check that phi is a homomorphism, you need to take two class. Suppose one is F and another one is F star. S1 B naught. Yes. Now, if you denote, if you rewrite this F and F star as by keeping in mind their the endpoints of their liftings, then you can write f, you can denote f by fn and f star as, suppose it is fm. That means their liftings will end at n and m respectively. So you can, where n is the endpoint of f tilde and m is the endpoint of f star tilde. Right. Then what you have, so then you can, so actually the observation is like that. So this and this, what will be the product of these two classes? What is your intuition tells? This will be f n plus m, right? So how you can do this? Just by defining a map G, defining a map G tilde T by just taking the translation of this. That means this map starts at n. Okay, and you can do this because e to the power 2 pi I n is again 1. So just at each integer you can translate the map, the path which starts at 0 and ends at n. Then you can have a map which starts at has a you can define a path which starts at n. Okay, so this is a path which starts at n. Not only that, you see that if you compose this map with p, then what you shall get? So this is your p of n plus f star of this. Now since p of t is e to the power 2 pi I t, then this translation will give you the same thing. So this is actually f star tilde t. Fine. And then p compose f star tilde will give you the map. What will be that? That is f star. Right? So this map, this path is the lifting of f star which begins at n. F star tilde is the lifting of f star which begins at 0. So G tilde is the lifting of f star which begins at n. So there are several liftings you can define, but once you specify a point, then that lifting is unique. Okay, and using this G tilde, you can say that just take the product of f tilde and G tilde. What will be that? This will be the lifting of f star this, which begins at 0. Now this begins at 1, b naught, and the value that means f of 0 is b naught. So that means this is the lifting of this one which begins at 0. But where it ends? It ends at the point where G tilde ends. That means, so it ends at G tilde 1. And what is G tilde 1? That means it is n plus f star tilde 1. But what is f star tilde 1? It is m. So it is n plus m. So therefore, phi of class F star class G is equal to phi of f star, sorry, this is f star this. Okay. So that means this is your, so the end point of f tilde star this. So that means it is n plus m. So therefore, phi of class F plus phi of class F star. And this proves that this phi is a homomorphism. That means phi becomes an isomorphism from the fundamental group of S1 onto the infinite cyclic group Z plus. So hence these two groups are isomorphic. So you have computed one fundamental group having non-trivial, so which is a non-trivial group, yes, right. And it is an abelian group. It is cyclic group. Now, since it is a cyclic group, then what will be the generator? The generator. So you can define one generator by using the covering map, just by restrict the map P onto the closed interval 0, 1. That is, if you take P naught as the restriction of okay. So restriction of P to this interval. Okay. So then this P naught is it is a loop based at B naught. Based at B naught. And the unique lift of P naught is a path that begins at 0 and ends at 1. Right? So then you can generate the group the fundamental group of S1 by using this P naught. I left this as an exercise. So this group, this is generated by this one. Okay. Okay. So now I need to okay. So in 10 minutes I can compute the fundamental group of torus. So how to compute this? Now I know that the torus is actually the space S1 cross S1, or you can this is the T that just you rotate just taking yes, a unit circle and just one small circle of radius, suppose 1/3, and then moving this small circle, this is your C1 and this is your C2, then move this C2 around this C1, then you will get a surface like this. Yes. Okay. And also you can apply the concept of quotient topology, and then you can construct a torus by using one unit square. Okay. Just okay. Yes. Just by gluing, first glue these two sides, the bottom edge and top edge, then you will get a cylinder. Okay. Then you will have a space like that. Okay. And then glue this circular rim together, and then you will have a torus. Yes. Fine. So how to get the fundamental group of torus? Just by proving one simple result and using the space S1 cross S1, because it is known to you now the fundamental group of the circle, which is Z plus, and using this one you can compute the fundamental group of S1 cross S1. That is the result which tells you that if you can prove that for two spaces X and Y, and if you specify one point from each space, that is, suppose you specify a point X0 in X and Y0 in Y, then you can prove that phi1 of X1 cross Y will be isomorphic to the direct product of the fundamental group of X based at X0 and the fundamental group of Y based at Y0. But how to get this one? Thus, by using projection maps. That is, since you have this product space, so you have the projection maps. Suppose one is P1, which is from X cross Y to X, and another one is from X cross Y to Y. So these are projection maps. And since this is a product topology, you have since you have defined a product topology on X cross Y, so these maps are continuous. So with respect to this continuous map, you can have homomorphisms. That is P1 star from to this fundamental group and P2 star from this one. Yes. And now with respect to these two homomorphisms, I can define one map from the fundamental group of the product space to the direct product of these fundamental groups. By assigning the value of this, so what will be that? So this will be defined as P1 star of class F and P2 star of this. Okay. That means this is P1 compose F and this will be P2 compose F, right? Now, this is easy to check that. Check on your own. This is very obvious that phi is a surjection. Phi is a surjection. And and since these two maps are homomorphisms, then you can easily check that psi is a homomorphism. So it remains to check the one-oneness of the map psi. So you need to compute the kernel of this homomorphism psi. That is, you need to find out those class F for which psi of this will go to the identity element of this direct product of groups. That means it is EX naught class and it is EY naught class, right? And by definition of psi, so it is actually, so it is P1 compose F class, which will be equal to EX naught class, and this is P2 compose F class, which is equal to this one. So that means P1 compose F is homotopic to EX naught. Suppose the homotopy is H, and P2 compose F is homotopic to EY naught. Suppose the homotopy is G. And by using these two homotopies, you can actually define a homotopy F from the unit square to the space product space X cross Y between the map F and the constant map at X naught, Y naught. What is the map? What is the path homotopy? The path homotopy is like that. This is actually H of S comma T, and this is G of S comma T. So these are very easy things. You can check this on your own. So this F is a continuous map, and this is a path homotopy between F. So this is a path homotopy between F and the constant map at X naught, Y naught, right? So this implies, so these two paths have the same class. So that means the kernel is a singleton, and this one, and this proves the result. So phi is an isomorphism from the fundamental group of the product space onto the direct product of their fundamental groups. And using this one, this is the corollary that pi 1 of the torus this is actually so isomorphic to the S1 B naught cross this. So that means it is isomorphic to Z cross Z. So thus the fundamental group of the torus is Z cross Z, right? Okay, so this, so I should stop here. Yes. Okay. So Sumanto, can you give the assignment of algebraic topology here? Okay, any question or queries? Yes.
Yes, sir.
Yes, Nityananda Babu, what you have mailed me, that how can you distinguish a disk and an annulus?
Yeah, yeah,
Actually,
yeah.
for these two spaces, you need to define deformation retract.
Okay, okay, okay.
Okay,
Okay,
you will see that
yes.
this space has fundamental group, a trivial group,
Okay,
but this annulus has the fundamental group Z,
okay.
which is
Thank you.
isomorphic to S1.
Okay.
Sorry, homeomorphic to S1. Because if you just take the deformation retract, then you will see that actually you can just span this circle
Oh, okay.
to this
Okay, thank you, sir.
external circle. Okay, so then
অভিষেক,
হ্যাঁ
এটা কি তুমি শুধু মার্কার্স থেকেই পড়ালে এই জায়গাটা আজকে একটু?
হ্যাঁ মার্কেটস থেকেই বেসিক্যালি, কিন্তু মার্কেটসে সবটা তো বলা নেই, এই আর কি, ওইভাবে বলা নেই।
হ্যাঁ, তুমি আর কি বই ফলো করলে সেটাই বলছি।
এছাড়া আপনার ধরুন আর্মস্ট্রং আছে, তারপরে আমার কাছে একটা বই আছে, এই ভদ্রলোকের নামটা আমি ঠিক জানি না, অ্যাকচুয়ালি 2014 আমি দিয়েছিলাম এই বইটা, এর নামটা আমি ভুলে গেছি ভদ্রলোকের। এটা খুব ভালো বই।
আচ্ছা, সফট কপি আছে না কপি বই? মানে
হার্ড কপি আমার কাছে আছে,
সফট কপি পেলে আমাকে দিও তো।
আজ আমি পাঠিয়ে দেবো। মানে এই ডিফরমেশন রিট্রাক্টটা বললে আর একটু ব্যাপারটা মানে আর একটু বেটার হতো আর কি, তাহলে আমি ওই R2 মাইনাস এইটাও বার করে ফেলতে পারতাম। So I can actually compute this one. So this is actually isomorphic to
S1.
So just using the fundamental group of S1, you can compute many fundamental groups of different spaces. So S1 will be the deformation retract of R2 minus. The deformation retract is like that. Just take one. I can simply tell you that just take one. Let us say in A, and you take one fat A.
নয়েজ আসছে কোথা থেকে এত?
Hello.
হ্যাঁ,
Then you can just take the deformation retract of this and squeeze the whole face into the skeleton, and you during deformation you need to fix your slim A, this A. Yes. So you will see that the fundamental group of the fat A is actually isomorphic to the fundamental group of this. Okay.
thank you very much. Nice lecture. Nice innovative lecture.
Yes.
Nice lecture.
Hello.
Hello.
এই অভিষেক,
হ্যালো।
হ্যালো, হ্যাঁ, তুমি কি সিঙ্গার অ্যান্ড থর্পের বইটার কথা বলছো?
না, সিঙ্গারা থম না, ওই যেটা আমরা সেই 2014 দিয়েছিলাম, ওই বইটা কার লেখা বললো তো, ভুলে গেছি।
সিঙ্গার অ্যান্ড থর্প লেকচার নোটস অন এলিমেন্টারি টপোলজি এন্ড জিওমেট্রি।
না, ওই বইটা নয়, তুমি ভুলে, তোমার
কোনটা?
সেই ওই ক্লাসিফিকেশন অফ সারফেসেস,
ও যেটা আমরা দিয়েছিলাম।
হ্যাঁ। ওটা কি না
যেটা
দাঁড়া
আমরা
ভুলে যাচ্ছি
দিয়েছিলাম। আচ্ছা 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 আচ্ছা, ওই বইটা। হ্যাঁ, ওটা ওটা কার লেখা? ওটা সফট কপি আছে আমার ধারণা, আমার কাছে তো কোথায় ছিল একটা।
আচ্ছা তাহলে
হ্যাঁ,
পাঠিয়ে, ওটা কার লেখাটা আমি ভুলে গেছি।
ওটা তোমার
ওটা মানে খুবই ভালো বই, খুবই ভালো বই।
হ্যাঁ হ্যাঁ হ্যাঁ, ওটা ভালো বই।
সুন্দর, তাহলে পাঠিও। হ্যাঁ,
এবং ওই বইটাও যদি কেউ কমপ্লিট করে ফেলতে পারে,
গ্যালিয়ার একটা গ্যালিয়ারের লেখা বই,
আচ্ছা
GALLIER।
ও আচ্ছা আচ্ছা আচ্ছা, ঠিক ঠিক, এইখানে
গ্যালিয়ার
বইটাতে আমার নাম
স্যার ওটা কি নাম? ক্লাসিফিকেশন অফ সারফেসেস।
এ গাইড টু ক্লাসিফিকেশন অফ সারফেসেস, আমার যত মনে হয়।
আচ্ছা,
হ্যাঁ হ্যাঁ একদম একদম।
নাম বানান একবার, স্পেলিংটা বলবে? হোয়াট ইজ দ্য স্পেলিং?
দেখুন চ্যাট বক্সে লিখে দিয়েছি, গ্যালিয়ার। হ্যাঁ,
থ্যাংক ইউ কৃষ্ণেন্দু।
হ্যাঁ ঠিক আছে। হ্যাঁ, এটা আমার মনে হয় আপনি পেয়ে যাবেন অনলাইন। হ্যাঁ
ঠিক আছে।
ঠিক আছে। এই অভিষেক,
হ্যাঁ বলো বলো।
আজকে বিকেলের লেকচারটা ক্যান্সেল করেছো, ওটা ইমেল পাঠিয়ে দিও।
হ্যাঁ এই আমি বলে দিয়েছি সবাইকে, আমি বললাম যে
email-
পরের রবিবার হবে 5 তারিখ।
হ্যাঁ হ্যাঁ, ইমেলটাও পাঠিয়ে দিও। হ্যাঁ,
না,
ইমেলটা পারি।
আজকে 3টের সময়টা হবে না?
না না,
না, আজকে
প্রধানমন্ত্রীর লেকচার আছে না, সেই জন্য ওটা আমরা ভাবলাম বাদ দিই। হ্যাঁ,
না, 3টে লেকচারটা হচ্ছে।
হচ্ছে না
হচ্ছে না।
ওটা হবে না আজকে।
আজকে লেকচার হচ্ছে না।
আচ্ছা, থ্যাংক ইউ।
ঠিক আছে।
অফিসে রাখলাম।
হ্যাঁ ফোন করছি আপনাকে একটু পরে।
ঠিক আছে।